Hello and welcome to Database Management Systems. I'm Chivita Christie, and in this video, I'm going to explain to you Armstrong's axioms in relational database design. So let's begin. Armstrong's axioms, where axioms mean rules of inference, which provide a simpler technique for reasoning about functional dependencies. I have explained what functional dependencies are in my previous video. And we know that it has something to do with how one column of a table depends on some other column. And you can recognize the value of a column in the table by using the value of some other column. And those things are known as axioms or rules which allow you to find out one dependency from another dependency. So when you want to find all logically implied functional dependencies from a given dependency, that would be where you will be using the Armstrong's axioms. And you'll understand the significance of this when you study normalization, because in normalization, we try to eliminate functional dependencies as much as possible. But we cannot do that unless some dependencies which are already extra can be removed. So Armstrong's axioms allow you to find something called a canonical cover, which I'm going to talk about in one of my later videos. But canonical cover allows you to reduce the set of dependencies that you have by applying some rules. And because they are already less, that's why your normalization becomes more effective and efficient. So let's see what these rules are. There are three main Armstrong's axioms. The first one being reflexivity, where if A is a set of attributes and if B is subset equal to A, then you can say that A determines B holds. So this is like creating a functional dependency that says A determines A, or it says AC determines C. It is understood that these things are correct because the right-hand side is a subset of the left-hand side, or the right-hand side is equal to the left-hand side. So in either of these cases, the reflexivity rule applies. Augmentation rule says that if A determines B holds and C is a set of attributes, then you can augment, which means you can attach C on both the left and right sides of the functional dependency and make it CA determines CB. And C can be either one attribute or a set of attributes. The third Armstrong axiom is transitivity rule, which says that if A determines B holds and B determines C holds, then A determines C holds. So notice how in A determines B on the right side, there is B, and in B determines C on the left side, there is B. So both the dependencies have B in common on opposite sides, and that's why you can conclude that A determines C. And these are the three basic Armstrong's axioms. But to make your work easier when you're trying to reduce functional dependencies, there are some additional rules that have been derived from these three rules, and we are going to see those. Once again, these rules are not limited to what I am presenting here. There are several rules, and many more rules can be derived from the three basic ones. I'm just going to show the ones that I'll be using in these videos. So the rule is called, the first additional rule we are going to talk about is union rule, which says that if A determines B holds and A determines C holds, then A determines BC holds. So in this case, you can see what's happening is quite simple, that in both A determines B and A determines C, on the left side, you have just A, which is common. And that's why you can merge the right side and make it BC. The next additional rule is decomposition, which is again a very important one, and we're going to use it quite extensively. It says that if A determines BC, then you can split it and make it A determines B and A determins C. So it's the exact opposite of the union rule. And then we have the pseudo-transitivity rule, which says that if A determines B holds and CB determines D holds, then AC determines D holds. So there is A determines B, which is given, and CB determines D is also given to you. And you can see what we did is replace the B, which is present in CB determines D, with A, because A determines B. So this is another one of the additional Armstrong's axioms. And now we're going to go ahead and prove these rules one by one. So the first one that we are going to prove is the union rule, which is A determines B and A determines C. Then we are going to prove that A determines BC. And the rules that are given to you are the basic ones. You cannot use the other rules. You can use only the three basic rules to prove this additional rule. So let us see how we can prove these rules. I'm going to show you the calculation that I am performing right here, so you can see it. And I'll also show you at the same time how to write a proper proof when such questions might appear in your examination. So the first step that I'm going to write is what is given to me, which is A determines B. This is given. So we need to mention that that is given. We have not just conjured it up here. Then the next thing I'm going to do is something very simple because I need to prove that A determines BC. So I need to get something on the left side and right side, and I'm going to augment A here. So it gives me A determines AB. So what I've done is applied the second rule, which is the augmentation rule. Augmentation of A in the first formula or equation that I got. I've augmented A on the left and right sides. Now the third thing that I'm going to do is use the A determines C dependency that I already have. So once again, it is important to mention given in the bracket. The next thing that I'm going to do is augment something here too. And in this case, I'm going to augment a B instead of an A. So it would give me AB determines BC. I think you know where I'm going now. Here, once again, I need to mention the rule that I have applied, which is augmentation of B in number 3. So this gives me this AB determines BC. And now if you look at the second rule and the third and the fourth one that I've derived, you can see here this is AB and this is also AB, which means I can indeed apply the third rule, which is transitivity, because my right side here is similar to the left side here. So this would lead me to AA determines BC, and it's fairly simple now, but we need to mention everything. So this is transitivity of rules 2 and 4. So that gives me transitivity. And as a sixth step, I could write down A determines BC without mentioning anything, because when two attributes are repeating, we can always remove one that is just set theory. So you can see this is the result that I was trying to prove, and I have proved it. You can see A determines BC is exactly what we were trying to prove. So that is how you can prove one rule by using the others present. Now the next rule that we are going to prove, let me just move on there. The rule is called decomposition rule, and we have already seen what it does. If it's doing the exact opposite of the union rule. So here, if A determines BC, then we can split it up and say that A determines B and A determines C. And once again, we are given the three basic rules to be used in order to prove the decomposition rule. So let's start by proving these two things one by one, because we have two. We are going to prove one first and then the next. So in this case, once again, I'm going to show you the calculation here. So as a first step, I'm just going to write down what is there in the what is there in the rule which I can use. So I can use A determines BC, which is given. As a second step, at this point, I'm just going to write my own dependency, which is BC determines B. And you'll notice this is done by using reflexivity. Because reflexivity can be applied anywhere. I could just make up my own dependency and say A determines A, because that's true. And so also BC determines B, because it doesn't matter that there's an extra attribute C which is not appearing on the right side. As long as there is B on left and B on right, I can make my own dependency whenever I want using reflexivity rule. Now, as a third step, you can see quite clearly now there is BC present here, BC here, which means I can once again apply transitivity rule as in the previous proof we did, and I can conclude that A determines B. This is once again transitivity between 1 and 2. Sorry for that. Yes, between 1 and 2. So this is transitivity between 1 and 2. And of course, you can do the same again, make your own dependency and write down BC determines C, just like you wrote BC determines B, because why not? If BC determines B, BC can also determine C. So this is once again the reflexivity rule in action. And once that is done, I can once again apply my transitivity rule here using number 1 where BC is on the right and number 4 where BC is on the left, which results in A determines C. So this is once again a transitivity rule applied to number 1 and 4. And you can see I have successfully proved that A determines C and also that A determines B, which I was supposed to prove. given that A determines BC, which was already given. So this is the rule, decomposition rule. This is the proof using the three basic rules which are available to us. And I'm also going to prove pseudo-transitivity and talk about canonical cover in my next video. So stay tuned for that. Thank you for watching.